Welcome back everyone to part 2 of tackling the MNIST image dataset with an artificial neural network. What we're going to do in part 2 is actually create our model and begin training the model. Let's get started. Okay, here we are at the notebook. We just saw what the image data looks like. Let's go ahead and start defining our model. This is going to be just a normal multi-layer perceptron model. We will say class multi-layer perceptron. And technically you can call this whatever you want, but we'll go ahead and inherit from nn.module, and then we'll set up our initialization or our init method. Remember, that's double underscores on both sides of that init. We'll pass in self, and then we're going to need an input size. So the input size here, remember, we're going to flatten out these images before feeding them into our artificial neural network. So 28 times 28 is equal to 784. So we have our initial input neurons, and then what we're going to do here is for the output size, recall there's 10 classes, the digits 0 through 9. So we should have 10 neurons, 1 neuron per class. And then finally, we'll say layers, and we'll make this a list that is adjustable. But we'll go ahead and, since we've experimented a little bit with what this perceptron model does, we'll go ahead and just say 120 neurons in the one hidden layer, and then 84 neurons in the next hidden layer. And then just as we did before, we'll say super dot underscore underscore init underscore underscore in order to basically instantiate this nn.module. And then we'll go ahead and start off with our fully connected layers. So we'll say self dot fully connected 1, and this is a linear layer, meaning everything's connected from one layer to the next. And we'll take our input layer and we'll go ahead and then connect it. And in this case, we'll go ahead and connect it to layers 0 or 120. So technically, I could manually write out 120 here, but this allows us new users to adjust whatever number of neurons they want in that next layer. So that's why we're just saying, go ahead and grab that first number of neurons in layers 0. Then we'll have another fully connected layer, FC2, and we'll say NN linear. And then this will go from layer 0 to layers at 1. So basically from 120 to 84, or whatever we happen to adjust that to. And then we'll say FC3. And again, fully connected, we'll go from layers 1 to the output, which is 10 neurons. And then finally, we define our forward method here. So we've taken self, and we've taken the actual data features, which is x. And we'll say x is equal to, take in f here. Remember, that's that functional import we did earlier. We'll use rectified linear unit as our activation, and then we'll pass in our first fully connected layer and pass in x. And then the result of that, we pass it into the next layer. So we say x is equal to f, rectified linear unit, into the next fully connected layer. Whoops, make sure that is balanced. And then after that, we finally have that last layer fully connected 3. So we'll say f, and in this case, we'll actually say self dot fc3 on x. And the reason we're not using rectified linear unit is because this is a multi-class classification problem. So what we need to do, instead of passing in to f.rectified linear unit, we'll go ahead and take in our data, pass it in to the first fully connected layer, pass it into the activation function of rectified linear unit. Take that result, pass it into the next fully connected layer, then pass that through the rectified linear unit activation function. Then take that, pass it through these fully connected layer, and then what we're going to do is we'll take that and we'll pass that through the logarithmic softmax activation function. So we could say f.log, and then we'll call softmax, pass an x, and if you take a look here, you need to specify a dimension, and if we expand this, we can see as we scroll down here that dim, or dimension, this is the dimension along which log softmax will be computed. And for this, that dimension, or that axis, should be 1. So we'll say dim is equal to 1. And technically, we could have gotten this and then also pass that in here and then just return that on a single line. But I really want to show you kind of the steps here. So we're doing a normal rectified linear unit activation, another normal rectified linear unit activation, and then for fully connected 3, we take that result, we're still passing it in through the layer, we're just passing it through a different activation function. And then technically, again, this line and this line could be combined to just return on a single line, but this separates out the steps so it's a little easier to read. And we're doing this because this is a multi-class classification. And we previously discussed that in a theory lecture. We'll go ahead and run that. And let's go ahead and set a seed so we can make sure that you get the same random initializations I do. We'll say model is equal to multi-layer perceptron, and then take a look at your model. And here we have this multi-layer perceptrons. Now, something I want to point out here is later on in this section of the course, we're eventually going to tackle this same problem, but move from an artificial neural network to a specialized convolutional neural network. And one of the main motivations behind that is the actual amount of parameters that an artificial neural network will have compared to a convolutional neural network. The convolutional neural network architecture that we will learn about later on is actually going to be more efficient and have a lot less parameters. If we take a look at our current artificial neural network, see here that we have 784 inputs being put into a full connection of 120 neurons, which are then fully connected to 84 neurons. And remember, each neuron is connected to every other neuron here. And if we were actually take a look at how many parameters we have, because recall, each of those connections has its own weight, and then we have each neuron having its own bias, we can actually say for param in model.parameters, go ahead and say param and then numel, which is number of elements, and we'll go ahead and print that out. So we print out the number of elements in all these model parameters. And here you can see we get a huge number of parameters. So this essentially are all the connections from 784 to 120. Then we have the 120 biases, then all the connections into that next layer, then the 84 biases, then all the connections into the next layer, so from those 84 neurons to those 10, and then we have those 10 output neurons. And if we were to sum this all up, you actually end up realizing that you have 105,214 total parameters. So those are all things that are being adjusted by the network. We're later going to see that we're going to have a lot less parameters if we use a more efficient convolutional neural network. So think of that as one point of motivation for moving to a convolutional neural network, especially when dealing with image data. And also recall that these images are actually quite small. They're only 28 by 28 pixels, and we're already kind of breaking 100,000 parameters. So just something to keep in mind as future motivation of moving on to a convolutional neural network. So we already saw that we have a ton of parameters here because we're using an artificial neural network. Let's finish off our network by defining a loss function and an optimizer. We will say here that our criterion is equal to nn.cross entropy loss, because this is a multi-class classification problem. And then finally, our optimizer is equal to torch, and we'll say optim, and we'll go ahead and use an atom optimizer for its efficiency. We'll pass in the model parameters, and the learning rate after experimenting with this a little bit, a nice one was 0.001. Now the last thing I want to know before we actually begin training the model is how we're actually going to flatten out the training data. If we take a look at the images variable we made before, recall that we did this, if you just scroll up, by running this little first batch command. Basically, just do one single for loop through the train loader and then break once you have that first set of images. Recall that that image's shape is 100 images by one color channel, and then the height and width, or width and height, of 28 by 28. So what I want to do is we're going to need to flatten out these images. Essentially, right now, the shape of this is 100, 128 by 28. And really what we need to do is we need to convert this so the shape is 100 by 784. Essentially taking these last three and combining this all into a single dimension. So we don't really care that there's a color channel since it's just grayscale, and we want to multiply 28 by 28. Essentially what we're going to do is just going to multiply the dimension sizes of 1 times 28 times 28 in order to flatten this out into 784 pixels, or 100 arrays, since there's 100 images, of this flattened out 784. The quickest way to do this is by using view. We say images, and I'm going to say view this as, we'll go ahead and keep the first dimension the same, 100 images, and then I will say -1, which is essentially a quick way of saying grab the rest of these dimensions and combine them into just a single dimension here. So when we say view 100 by -1, we get back this tensor, and if I were to check the shape of this, it gives me back 100 images where they've been flattened out to 784, essentially taking these last three, and because we called -1 here, it combines that all into one single dimension. So later on, you'll see me calling .view 100 by -1. Okay. Coming up next in part 3, we're actually going to set up the training of the model. So far we've created the model, understood how we're going to flatten out our images. Up next, we'll train the model, and then we'll see how to evaluate it. I'll see you at the next lecture.